Welcome dear students. In today's lecture we are about to discuss numericals on electric flux and numericals on Gauss's theorem. So first of all, a recap for electric flux. Total number of electric field lines which pass through a given surface is known as electric flux. If electric field is uniform, then electric flux is straightway given as dot product of E vector and A vector. For a non-uniform electric field, flux is integration of electric field with small area vectors drawn on the given surface. So E dot ds is to be added, integrated. Flux is a scalar quantity told in last videos. SI unit of flux is voltmeter or Newton meter square. Please note down these points. It would be easier to understand the further parts. Okay, one question from NCRT. Consider a uniform electric field 3 into 10 power 3 I cap Newton per coulomb. Newton per coulomb is SI unit of electric field. I cap means electric field is directed along positive x-axis. Question 1 is what is the flux of this field through a square of 10 centimeter side on whose plane is parallel to YZ plane. So let me draw a diagram to make it completely understood. Please, while you note down, underline the main issues. First of all, electric field is 3 into 10 power 3 along I cap, means along x-axis. Square has side equal to 10 centimeter, which would be equal to 0.1 meter. And plane of the square is parallel to YZ plane. This is your YZ plane. I am moving the cursor. Okay. Then B part, what is the electric flux through the same square if the normal to its plane makes an angle 60 degree with x-axis? So second part we'll discuss later. Let us address first part. Just assume that it is the corner of your drawing room, x-axis, y-axis, z-axis would be easier to understand. These are just walls and this is your floor part. So you can well imagine the picture in your mind. Electric field as told is along I cap, means along positive x-axis. Okay, now the area which is in the form of a square of side 10 centimeter, that is parallel to YZ plane. So area drawn in yellow is lying in YZ plane, but as told so many times, area is a vector quantity and in direction it points perpendicularly to the plane. So area vector is directed along x-axis. So there is 0 degree angle between electric field and area. So area pointing along x-axis means you have to write first its magnitude. 10 centimeter means 0.1 meter. Square means side square is equal to area. This is magnitude of area. Direction of area is I cap. So we have written area. Electric field is already given in SI units. So we have written both area vector and electric field vector in SI units. Now flux is given as E dot A. So you have to take dot product of these two vectors. Since angle between these two is equal to 0 degree, so straightway E into A into cos 0. Cos 0, that is 1. So just multiply and you get the answer. Second part is what is the electric flux through the same square if the normal to its plane makes an angle of 60 degree with x-axis. So I have drawn another square. Its area vector is pointing downwards, not exactly downwards, but at some angle. Electric field and area vector. This area vector is making an angle of 60 degree with x-axis. 60 degree with x-axis means 60 degree with electric field too, because electric field is pointing along positive x-axis. Okay, so angle between A and E is given to be 60 degree now. So electric flux would be same area, same electric field, but angle between the two now is 60 degree. Cos 60 you know is equal to half. So rest of the part same. Just half of 30 would be equal to 15 volt meter. Now I am addressing a similar question from NCERT in which same electric field is to be used, but now we are given a cube of side 20 centimeter which is oriented so that its faces are parallel to the coordinate system. So this is our cube. This blue face and its opposite face backside are parallel to xy plane. Red one is parallel to YZ plane and the black one is parallel to XZ plane. So this is how the cube was to be oriented. Now let me draw again electric field direction E along positive x-axis, backside, upper side, front side, lower side. So you notice that field lines are parallel to this plane. Parallel to this plane means if area vector is drawn vertically up, then angle between area and electric field is 90 degree. Please check. Here area vector is drawn towards right hand side. Here area vector is drawn towards left hand side, means perpendicular to the plane. And area vector here would be at right angle to the electric field. Okay, now see, for these four faces, 1, 2, bottom and back, angle between E and A is 90, cos 90 is 0. So for four faces, 1, 2, bottom and back side, flux would be 0, 0, 0, 0 as cos 90 is equal to 0. Now we are left with the red face and its opposite face, which is not visible here. On red face, angle between area vector and electric field vector is 0. So E into A into cos 0. Now come to the opposite face of the red one. Area vector is pointing left, electric field is pointing right. Angle between the two is equal to 180 degree. However, electric field size, electric field area, and here they are same. So cos 180 is minus 1, told so many times. Cos 0 is equal to 1. So this is EA, this is minus EA, EA and minus EA cancel out, and which gives total electric flux equal to 0. Hope you understood it well. If there is any problem, you can rewind, go back again. Next question. In a region of space, electric field is given by 8i cap, 4j cap, 3k cap, and an area of 100 meters square is lying in xy plane. The total electric flux through the given area in volt meter is. So let me explain through same figure again. XYZ axis. Area of 100 meters square is lying in XY plane. So this is your XY plane. So we have an area of 100 meters square already in SI units. Area vector would point perpendicularly this way. Electric field is having X component, Y component as well as Z component. So area can be written as magnitude 100, direction along Z axis, that is K cap. Okay, now electric field is already given. You have to take the dot product. So if vectors are given in component form I cap, J cap, K cap, then while taking dot product you need not use cos theta. You simply have to multiply I cap with I cap, J with J, K with K. So here I cap is missing, J cap is missing, only K cap is there. K cap dotted with K cap is equal to 100 into 3 equal to 300 unit volt meter. Okay, next question. A cylinder of radius r and length L is placed in uniform electric field E parallel to the axis of the cylinder. The total electric flux through the curved surface of the cylinder is. Electric field is parallel to the axis of the cylinder. This is axis of the cylinder. Electric field is pointing this way. So this is your E. And you require electric flux through the curved surface of the cylinder. This is your curved surface. So curved surface, if you draw any small area here, then it would point vertically up. So angle between E and A is 90 degree, and it would happen to be same all over the curved surface. Okay, you got the idea. I would draw more vectors, but this area was not required. So we have to find electric flux only through the curved surface. So angle between A vector and E vector. Everywhere on the curved surface is 90. Angle between E and A is 90 degree everywhere on the curved surface. So electric flux is equal to 0. Now we will switch over to Gauss's theorem. First of all, a quick recap. According to Gauss's theorem, total electric flux crossing a given closed surface was equal to 1 by epsilon times the charge enclosed by the surface. Flux is given as E dot ds, but since surface was closed, so integration was to be carried out over the curved surface, and it was equal to 1 by epsilon times the charge enclosed. So this is your 9th question in the assignment sent to you. The electric flux through the surface shown in the following figures. The surface is drawn in irregular manner, somewhere ellipse, somewhere sphere, somewhere irregular path. But each time total charge inside the surface is same. Since charge enclosed is same, Gauss's theorem says total electric flux is equal to 1 by epsilon times the charge enclosed, which means electric flux is just determined by how much charge is inside the Gaussian surface, inside the closed surface. So whether it's lying here or at the center doesn't matter. But only thing is it must lie inside the given surface. So in all the 4 cases, the charge lying inside the surface is equal to plus Q. So that means electric flux is same in all the figures. That is 4th option is correct option. Okay, let me proceed further. Another points which we came across in the derivation. Applications of Gauss's theorem. One was electric field due to a line of charge which was equal to lambda by 2 pi epsilon naught r. Lambda represented charge contained per unit length. Electric field due to a uniformly charged sheet, single sheet, was sigma by 2 epsilon naught. Sigma was surface charge density, charge contained per unit area. And electric field due to a spherical shell, we had gone through 3 cases. One was if the given observation point is outside the charge sphere, then it behaved like a point charge lying at the center of the sphere. So formula was Q by 4 pi epsilon naught r square. Second, if the given point, observation point, lies on the surface of the sphere, then r became equal to radius of the sphere, then capital R square here. And if you go inside the sphere, the charge enclosed was 0. On applying Gauss's theorem, we got electric field inside the sphere equal to 0. So before we proceed further, please note down these points. Okay, here is a simple question first. Figure shows the field produced by 2 point charges plus Q and minus Q, which we usually refer as electric dipole. Find the electric flux through each of the closed surfaces A, B, C, and D. So Dipole means charges are equal and opposite. Plus Q, minus Q. You are given four surfaces. A is a sphere drawn about plus Q. B, again a sphere drawn about minus Q. C is a large surface, purple shape, which encloses the whole electric dipole. And D, this orange one, which doesn't enclose any charge. I think you can now apply Gauss's theorem. If you speak out before me, that would be better. So electric flux through A would be through A. A encloses only plus Q, so Q by epsilon naught, plus Q by epsilon naught. B encloses a charge minus Q, so minus Q by epsilon naught. C encloses total charge of plus Q and minus Q, that means 0. And D doesn't enclose any charge. Hence, according to Gauss's theorem, 1 by epsilon naught times into 0. Answer is 0. Similarly, there was question number 3 in the given assignment to you. An arbitrary surface means an imaginary surface encloses a dipole. Now you know the answer. What is electric flux through the surface? So it is basically in the question we are referring to surface C. C encloses a dipole, total charge enclosed is 0. That means electric flux is equal to 0. Okay. Question number 5 of the assignment given to you. You are given 4 charges 2Q, Q, minus Q and minus 2Q. Charges are plus 2Q, plus Q, minus Q and minus 2Q. Describe how would you place a closed surface that encloses at least the charge 2Q and perhaps the other charges so that the net electric flux through the closed surface is 0. 2Q is to be placed in all the cases A, B, C. 2Q has to be inside the surface. How would you manage all these remaining three charges, so that total electric flux is 0? You notice that sum of these charges is already 0. So if we enclose all of them in a closed surface, could be a balloon, then total electric flux is going to be 0, as the total charge enclosed is 0. In second case, we need a flux of 3Q by epsilon naught. 2Q is already inside. So we need a total charge of 3Q inside the surface. 3Q means 2Q plus Q. So enclose these two inside the surface and leave these two outside. So as shown here. Okay, last part. We need a flux of minus 2Q by epsilon. That is possible only if we have a total charge of minus 2Q enclosed inside the surface. Try to guess before me, better it would be. How to get a total charge minus 2Q inside the Gaussian surface? One way is place this one inside and place all these outside. One more way is there. Yes, please answer. Keep 2Q out and have minus 2Q plus Q and minus Q in, because in this case total charge plus Q and minus Q cancels out and total charge left inside is minus 2Q. So there is two possible ways. So I am showing here one, the other you would draw yourself. So what you have to do, either keep minus 2Q in and keep others out like this, or you can keep minus 2Q plus Q and minus Q in and keep 2Q out. In that case also you will get the same answer. Okay, so another question on electric flux, Gauss's theorem. 10th question, of the given assignment. Consider an infinite line of charge having a uniform linear charge density and passing through an axis of the cylinder. So here is the linear charge distribution. Question is, what will be the effect on flux passing through the curved surface if the portion of the line charge outside the cylinder is removed? If we remove this part, let me draw a new one. Outer part of the wire is removed. What would be the effect on the electric flux through this curved surface? So as you know, Gauss's theorem says the total electric flux through a closed surface is equal to 1 by epsilon times the charge enclosed by the surface. So since charge enclosed doesn't change on removing this part and this part, this is outside the surface. If the charge outside the surface is not affecting our result, so on removal of this charge, electric flux is not going to change. So answer is no change. Hope you got me. The charge outside the cylinder is not mentioned in Gauss's theorem. We are supposed to consider only electric flux due to charge inside the surface. So total electric flux through the cylinder doesn't change. Okay, this is a question MCQ type in which there could be more than one choice is correct. Refer to the arrangement of charges and a Gaussian surface. Dotted line is Gaussian surface. Charge is Q lying at the center. Another charge minus 2Q is lying inside the Gaussian surface. Another charge 5Q is lying outside the surface. So we have to choose which of the following choices or choice are correct. So first choice, total flux through the surface of the sphere is minus Q by epsilon naught. So very easy. Total charge enclosed by the Gaussian surface is Q plus minus 2Q. So summing up would give minus Q. So total electric flux is equal to 1 by epsilon times charge enclosed. Charge enclosed is minus Q. That means correct answer first is okay. Field on the surface of the sphere is minus Q by 4 pi epsilon r square. This one would have been correct if there is a symmetry of the charge distribution, or this minus 2Q also lies at the center of the sphere. In that case, total charge lying here is minus Q, and electric field at same distance is obviously equal. So everywhere electric field would have been minus Q by 4 pi epsilon r square. But minus 2Q is not lying at the center. So due to non-symmetric charge distribution, electric field here, this is so-called asymmetric distribution of charge, non-symmetric distribution of charge. As a result, electric field at various points of the Gaussian surface is not going to be same. So maybe somewhere you may get it as minus Q by 4 pi epsilon r square, but not everywhere. So second choice is incorrect choice. Third, electric flux through the surface of the sphere due to 5Q is 0. Obvious. 5Q charge is lying outside the Gaussian surface. Outside the Gaussian surface means electric flux due to 5Q would be 0. Very simple. If 3 lines are entering the Gaussian surface, then 3 would be leaving from this side. Entering flux is taken as negative, leaving flux is taken as positive. So if 3 lines enter the Gaussian surface from this side, so flux would be minus 3, then same 3 lines would leave the Gaussian surface on the other side. So plus 3 and minus 3 equal to 0. Otherwise also, as per Gauss's theorem, the charge which is not enclosed by the Gaussian surface doesn't contribute any electric flux. So flux due to 5Q charge is 0. Correct choice. Fourth one. Field due to the minus 2q on the sphere is same, not same, because these points are closer to minus 2q, so stronger electric field. These points are far away from minus 2q, so weaker electric field. So electric field due to minus 2q is not same everywhere on the Gaussian surface. So fourth choice is also incorrect choice. So options 1 and 3 are correct. Okay, now one question from H.C. Verma. Question number 4 in your assignment. A large plane charge sheet having surface charge density sigma equal to 2 into 10 power minus 6 coulomb meter square lies in xy plane. So this is your xy plane, and here we have a sheet, large plane sheet. So I have drawn large one. Surface charge density 2 into 10 power minus 6 coulomb per meter square. Find the electric flux of the electric field through a circular area of radius 1 centimeter lying completely in the region where something is missing here, x, y, z are all positive, and making an angle of 60 degree between normal and electric field direction and normal to the given circular area is making angle 60 degree with z axis. So let me first of all simply make you recall that due to positively charged sheet, electric field is away from the charge and is uniform in nature. So electric field lines are directed towards u but can't be drawn towards u. So we have to draw along z axis. So this is the direction of electric field, and field lines are parallel as told in the derivation. Electric field due to a uniformly charged sheet doesn't depend upon R, means as you keep moving away and away from the sheet, electric field remains same. Okay, this was about electric field. Now the area vector. So assume you have a frying pan or cooking tawa, to have a good imagination, and it is oriented, radius is as given 1 centimeter, so 1 centimeter radius, and area vector means which is perpendicular to the plane of the tawa, that points at 60 degree angle with z axis. So angle between electric field lines, you can see electric field is also along positive z axis. So angle between E vector and A vector is 60 degree. Okay, now you know electric flux is equal to E dot A, means E into A into cos theta, cos of 60 you have to use, and further is very simple, sigma by 2 epsilon naught electric field due to a uniformly charged sheet into area means pi r square. So let's substitute the values. E equal to sigma by 2 epsilon naught, area equal to pi r square, cos 60 you know 1 by 2. What change I have made here to write 1 by 4 pi epsilon naught, which is easier to substitute, I have multiplied and divided by 2 pi. That would make your treatment easier, calculations easier. 1 by 4 pi epsilon naught, that is easier to substitute. Numerator, in numerator you have to write 9 into 10 power 9. Sigma is given, and also told repeatedly pi square is approximately equal to 10. You may write pi square equal to 10. So 1 by 4 pi epsilon naught, 9 in 10 power 9, value of sigma given 2 in 10 power minus 6, then 2 and pi square equal to 10, then radius square, radius is 1 centimeter, you have to change it to meter. So 1 by 100 means 0.01, and r square means 0.01 square. into cos of 60 means half. So I leave the calculation to you, and answer is 18 volt meter. So that's all in today's lecture. If you have understood all the questions, enjoyed the lecture, please give a like, share the video with other students, and subscribe the channel.